Hi friends, in the continuation of data science interview question answer series, we are moving to question difference, decision tree and pruning, post pruning. In decision tree, goal is to continue growing the tree until all leaf nodes are pruned or contain a minimum number of samples. In pruning, to reduce the size of tree by removing branches that provide little power in generalization. Primary result decision tree, a complex deep tree with potentially thousands of nodes. In pruning, a simpler shallower tree with better generalization capability performing on training data. Decision tree perfect or near perfect accuracy, low training error. Pruning slightly high training error compared to the unpruned tree. Risk. Decision tree high risk of overfitting to training data, capturing noise and outlier. Pruning mitigate the risk of overfitting and improve performance on unseen data. Bias variance. Decision tree low bias, high variance. Pruning increase bias slightly but reduce variance significant. Cost function. Decision tree minimize the error impurity, example Gini impurity or entropy at each split. Pruning minimize the total error on separate validation set or function of error plus tree complexity. Mechanism. Decision tree. Greedy approach. Find the best split at the current node independent of future split. Pruning. Evaluate a sequence of subtree, prune tree to find the one with the best generalized performance. Alternative. Decision tree can be controlled using pre-pruning technique, example max step, mean sample per leaf during growth. In pruning, post-pruning like cost complexity pruning is often more effective because it can see the full tree structure first. Moving to question, decision between one-hot encoding and label encoding. Output type one-hot encoding a sparse binary vector for each category, label encoding a single integer number for each category, number of features. One-hot encoding create n new binary features columns where n is the number of unique categories. Label encoding creates one new feature column. Scale of data. One-hot encoding leads to high-dimensional sparse dataset. Label encoding leads to low-dimensional dense dataset. Handling categories. One-hot encoding does not introduce false ordering. All categories are treated as independent. Label encoding introduces a arbitrary ordinal relationship 3 to 1 between categories which is misleading for nominal data. Memory uses. One-hot encoding high memory uses for large high coordinate categorical variable. Label encoding low memory using best use case one-hot encoding for nominal unordered categorical variable example colors city name is most ML algorithm. Label encoding for ordinal ordered categorical variable example size small medium large or as input in the tree based model. Problem mitigation. One hot encoding mitigates the problem of algorithm treating categories as having quantitative rank. Label encoding should only be used if ordinal nature is meaningful to target variable. Example, categories red becomes 100. In label encoding categories, red become 1. Moving question difference between bias in data and bias in model. Source human, societal, or data collection flaws. Example lack of diversity in training data, historical time, discrimination in labels, bias in model. The inherent limitation of chosen algorithm to approximate the true functions, simplification, impact. Bias in data, the model learned and precludes unfair or skewed decision making against certain groups. Bias in model, the model unfits the data, resulting in the consistent systematic error, underestimation or overestimation. Ethical aspect, bias in data, high ethical concern directly relates to fairness, accountability and transparency. FAT in bias model, purely technical concern related to bias variance trade-off. Mitigation in ML, bias data requires fairness audits, de-biasing techniques, example resampling, adversarial de-biasing, and diverse data sourcing. Bias in model requires increasing model complexity, example using a non-linear model, adding more feature or reducing realization. Consequences, bias in data can lead to discriminatory outcome in leading hiring or criminal justice practice. Bias in model leads to poor predictivity, accuracy, and unfair underperformance on both training and test data. Time frame often integrated in the historical data and requires manual intervention to fix a characteristic of the chosen algorithm and its hyperparameter. Example of error, a hiring model training on the hierarchical historical data systematically rank female applicant lower due to the gender imbalance in the past hire. Bias model, a linear regression model is used to fit parabolic relationship resulting in systematic error at the extremes. Evaluation bias in data assessed using fairness matrix, example demographic party equalized odds on sensitive attributes. Bias in model assessed using the training and validation loss. High loss suggest high bias. Please like, subscribe, and share. Thank you.